Tonight, if you go outside and look up, almost everything you see is a kind of time machine. The light from the nearest bright star left it years ago, and some of the faint smudges up there set out on their journey toward your eye before there were humans to look back at them. You are not really seeing the sky as it is. You are seeing the sky as it was, all of it arriving at once. A single layered image stitched together out of light of wildly different ages. And for almost the whole of human history, nobody had any idea that this was happening, because nobody knew how far away any of it really was. This is the story of how we found out. Not just what the stars are, though we will get to that, and it is stranger than you might guess, but the longer and harder question hiding underneath it, which is the simple sounding one a child asks and almost no adult can answer. How far away is that? How do you measure the distance to something you can never touch, never visit, and never reach? The history of astronomy is really the history of people slowly inventing ways to answer that question. And every time they answered it, the universe turned out to be far bigger than anyone was ready for. So, to understand how we got here, with our talk of galaxies and an expanding universe and planets around other suns, we have to go back to a time when the sky was not a place at all, but a ceiling. Because that is how it started. For most of human history, the sky was understood as a dome over a flat world, with the lights stuck to it like decorations. And the idea that those lights might be enormous, blazing things impossibly far away, would have sounded like madness. What people did notice very early is that the sky was not random. It moved, and it moved with a regularity you could set your life by. And that regularity was the first thing that turned looking up into a science. The earliest people who really studied the sky carefully, as far as we can trace, were in Mesopotamia, in the region of ancient Babylon, more than 2,500 years ago. They were not doing astronomy for the love of it. They were doing it because the sky was a calendar and a clock, and getting it right meant knowing when to plant, when the river would flood, and when to hold their festivals. So they watched night after night, year after year, for centuries, and they wrote it all down on clay tablets. And over time, they built up something genuinely powerful. They could predict. They worked out the rhythms of the moon, the patterns of the planets, and even, eventually, when eclipses were likely to come, not because they had any picture of what an eclipse was, but because they had watched long enough to see the cycle repeat. This is worth sitting with because it is a kind of science we do not usually credit. They had no model of the heavens, no idea what the moon or sun actually were, and yet by sheer patient record keeping, they could tell you what the sky would do. They had found the pattern without the explanation. The next great leap came from the ancient Greeks, and what they added was the explanation, or at least the attempt at one. The Greeks were not satisfied with knowing that the sky repeated. They wanted to know why, and they wanted a picture, a model, a machine of some kind behind the lights. And some of the things they figured out, with nothing but careful thought and simple tools, are still astonishing today. By around the 5th century before the Common Era, educated Greeks had already worked out that the earth is a sphere, not a flat disk, and they had good reasons for it. They noticed that as you sail south, new stars rise into view that you could not see from home, which only makes sense on a curved world. They noticed that during an eclipse of the moon, the shadow the Earth casts on it is always round, and the only shape that always casts a round shadow, no matter how you turn it, is a sphere. They were reading the shape of their own world off the sky, and they got it right 2,000 years before anyone sailed around it. Then there is the one story from ancient astronomy that, if you have never heard it, is going to sound almost too good to be true. Around the year 240 before the Common Era, a Greek scholar named Eratosthenes, who ran the great library at Alexandria in Egypt, measured the size of the entire earth, and he did it with a stick and a shadow and some clever thinking. He had heard that in a town to the south called Syene, on a particular day of the year, at noon, the sun shone straight down to the bottom of a deep well, meaning it was directly overhead and cast no shadow at all. But he knew that on that same day, at noon, in Alexandria to the north, a vertical stick did cast a shadow. If the earth were flat, the sun's rays would hit both places at the same angle, and there would be no difference. The only way one place could have no shadow while another did was if the ground was curved between them. So he measured the angle of the shadow in Alexandria, which came out to about 7 degrees, roughly a 50th of a full circle, and he knew the distance between the two cities. From just that, a shadow angle and a distance, he calculated the circumference of the whole planet, and his answer was within a few percent of the real number we measure today with satellites. A man with no telescope, no spacecraft, no photographs of the Earth, measured the size of the world from the length of a shadow and very nearly nailed it. That is the moment astronomy became a science of real, hard numbers. The Greeks pushed further. One of them, named Aristarchus, made an even bolder guess. He argued, far ahead of his time, that the Earth was not the center of everything at all, but that the Earth and the planets went around the Sun, and that the Sun was much larger than the Earth, which is why it made more sense for the smaller thing to circle the bigger one. He even tried to measure how far away and how big the Sun was, using the geometry of the moon's phases. And although his tools were too crude to get the right numbers, his reasoning was sound. He had the right idea nearly 18 centuries before Copernicus, but the idea did not catch on, partly because it simply did not feel right. You do not feel the earth moving, and so the obvious, common sense view won, and the earth stayed at the center for a very long time. The astronomer who shaped how people saw the sky more than any other ancient figure was Hipparchus, who worked in the 2nd century before the Common Era and is sometimes called the father of scientific astronomy. He was a tremendous observer and a careful measurer, and he did something that sounds modest, but was a genuine gift to everyone who came after, which is that he made a catalog of the stars, recording the positions and the brightnesses of hundreds of them as precisely as he could. He even sorted the stars into ranks of brightness, and a version of that system where the brightest stars are first magnitude and the faintest are sixth is still used by astronomers today. But the most remarkable thing Hipparchus found came from comparing his own careful measurements to records made by Babylonians long before him. He noticed that the whole sky had very slowly shifted, that the position where the sun sits against the stars at the start of spring had drifted a tiny amount over the centuries. He had discovered that the earth itself wobbles very slowly, like a spinning top that leans and turns, so that the entire sky appears to creep around over a cycle of about 26,000 years. To detect a motion that takes longer than the entire span of recorded history to come around once, using nothing but old records and naked eye measurements, is a staggering piece of work. All of this Greek astronomy was gathered up several centuries later by a man named Ptolemy, who worked in Alexandria around the year 150 of the Common Era, and who wrote the single most influential astronomy book in history. It is usually called the Almagest, and it pulled together everything the Greeks knew about the heavens into one enormous, careful system, complete with a star catalogue and the mathematics to predict where the planets would be. Ptolemy's universe had the Earth sitting still in the center, with the sun, moon, and planets going around it. The problem he had to solve was that the planets do not move smoothly. They sometimes appear to slow down, stop, and drift backward for a while before going forward again. Those strange little loops in the sky. To explain this while keeping the Earth in the center, Ptolemy built a complicated arrangement of circles riding on circles, where each planet moved on a small circle whose center moved along a larger circle. It was intricate and a bit ungainly, but here is the thing that matters. It worked. It predicted the positions of the planets well enough to be useful, and so it stood as the accepted picture of the universe for around 1400 years. Almost no scientific idea in history has ever reigned that long. For nearly a millennium and a half, if you wanted to know where the planets would be, you used Ptolemy. Before we leave the ancient world, there is one object worth pausing on, because it shows just how sophisticated this old astronomy really was. In the year 1901, divers exploring a shipwreck of a Greek island called Antikythera pulled up a corroded lump of bronze that did not look like much. It took most of a century and modern scanning technology to understand what it was, and the answer stunned everyone. It was a machine, a device of interlocking bronze gears, more than 30 of them, built more than 2,000 years ago, and it was an astronomical calculator. You turned a handle, and the gears would show the positions of the sun and moon, track the phases of the moon, follow the cycles of the planets, and even predict eclipses. Nothing else of that mechanical complexity is known from the ancient world, and nothing approaching it would appear again for well over 1,000 years. It tells us that ancient astronomers did not just watch the sky, they had built a working model of it, a little brass universe you could hold in your hands and crank forward in time. Then, for a long stretch in Europe, astronomy mostly held still. The careful work of keeping it alive, refining it, and pushing it forward during these centuries happened largely in the Islamic world, where scholars translated and preserved the Greek texts, made their own precise observations, built better instruments, and improved the star catalogs. We carry a quiet reminder of this every time we name a star, because a great many of the bright stars in our sky still carry the Arabic names those astronomers gave them, names like Betelgeuse, Rigel, Aldebaran, and Vega. The words themselves are a kind of monument to the people who kept the lights catalogued while Europe was looking elsewhere. The thing that finally broke Ptolemy's long reign was not a new observation at first, but a new idea, and it came from a careful church official in Poland named Nicolaus Copernicus, who published it in the year 1543. On his deathbed, Copernicus suggested taking the Earth out of the center and putting the sun there instead, with the Earth becoming just another planet going around it. The strange backward loops of the planets, the ones Ptolemy needed all those circles to explain, fell out naturally in this new picture, simply as a result of us passing the slower outer planets, or being passed by the faster inner ones, the way a faster car overtaking a slower one makes the slower one seem to slide backward for a moment. It was a simpler, cleaner picture, and that simplicity was a clue that it might be true. But Copernicus had no proof, and his model still was not perfect, because he kept the old assumption that the planets moved in perfect circles, which they do not. The proof and the real revolution came in the early 1600s with the arrival of a tool that changed astronomy forever, the telescope. When an Italian named Galileo Galilei pointed one of the first telescopes at the sky in the year 1610, he saw things that simply did not fit the old picture of a perfect Earth-centered heavens. He saw that the moon had mountains and craters, that it was a rough, rocky world, and not a flawless heavenly orb. He saw that Jupiter had 4 little moons of its own circling it, which proved plainly that not everything in the universe goes around the Earth. And he saw that the planet Venus went through a full set of phases, like our moon, growing from a thin crescent to a full disk and back, which only makes sense if Venus orbits the Sunday. The telescope had turned the heavens from a painting on a ceiling into a collection of real worlds, and the evidence for the sun-centered system was suddenly there for anyone willing to look. At nearly the same time, a German astronomer named Johannes Kepler took the most precise measurements of planetary positions ever made, gathered patiently by a Danish observer named Tycho Brahe, and used them to figure out the true shape of the orbits. After years of struggle, he found that the planets do not move in circles at all, but in ellipses, slightly squashed ovals, with the sun sitting off to one side. With that one correction, the predictions became almost perfect. And then, later in the same century, Isaac Newton explained why, showing that a single rule of gravity the same force that makes an apple fall, holds every planet in its elliptical path around the sunday. Within about 100 years, astronomy had gone from a system of mysterious circles to a clockwork solar system that ran on one understood force. The sky was no longer just predictable. It was, for the first time, explained. But notice what astronomy still did not know, even after all of this. We knew the shape of the solar system and the rule that governed it, but we had almost no idea how big it was in real terms, and we had no idea at all how far away the stars were. The stars were still just points of light, and they could have been anything, small nearby lamps or enormous distant fires. The whole grand question of distance was still wide open. And the next few centuries are the story of slowly, painfully prying it open. The first thing that happened is that the solar system itself got bigger, and it did so in a way nobody expected. For all of recorded history, people had known of exactly the same handful of planets you can see with the naked eye out to Saturn, and it never occurred to anyone that there might be more because for thousands of years there simply had not been. Then, in the year 1781, an astronomer named William Herschel, sweeping the sky with a telescope he had built himself, spotted something that moved against the background stars, something that turned out to be an entire new planet, far beyond Saturn, which we now call Uranus. In a single night, the known solar system had doubled in size. Suddenly, it was clear that the sky was not a finished, fully mapped thing. There was more out there, waiting, and bigger telescopes might find it. The discovery of the next planet after that is one of the great triumphs of the whole field, because it was found not by looking, but by mathematics. Astronomers noticed that Uranus was not quite following the path Newton's gravity said it should. It kept drifting slightly off course, as if something unseen were tugging on it. Rather than abandon Newton, two mathematicians, working separately, used the size and direction of those tiny tugs to calculate where an unknown eighth planet would have to be to cause them. They handed the prediction to an observatory. The telescope was pointed at the calculated spot, and there, almost exactly where the mathematics said it would be, sat the planet Neptune. It was found in the year 1846. Think about what that means. A planet that no human eye had ever knowingly seen was located first on paper by the pull of its gravity on its neighbor, and only then confirmed in the sky. Newton's law of gravity had become so trusted that it could be used to find new worlds in the dark. While the solar system was growing, a completely different and deeper question was finally being cracked, the oldest one of all, the distance to the stars. The method that finally worked is something you use without thinking every moment of your life, and you can feel it right now. Hold up a finger at arm's length, close one eye, then switch eyes and watch your finger jump against the background. That apparent jump caused by viewing from two slightly different positions is called parallax, and it is the basis of all depth perception. The closer the object, the bigger the jump. Astronomers realized that the Earth gives them two viewing positions automatically because over the course of half a year, the Earth moves to the opposite side of its orbit around the Sun, a baseline of many millions of miles. A nearby star, viewed from these two ends of the Earth's orbit, should appear to shift its position very slightly against the far more distant background stars, and from the size of that shift, you could work out the distance using nothing more than the geometry Eratosthenes would have recognized. The trouble was that the stars are so monstrously far away that the shift is unbelievably tiny, far too small for the naked eye and beyond the reach of telescopes for centuries. It was not until the year 1838 that anyone finally measured it, when a German astronomer named Friedrich Bessel managed to detect the minuscule yearly wobble of a star called 61 Cygni and calculate its distance. The answer was almost incomprehensible. The star was so far away that its light, traveling at the fastest speed there is, took about 11 years to reach the Earth. And that was one of the nearest stars. For the first time, humanity had a real measurement of the gulf between the stars. And the gulf was so vast that we needed a new kind of ruler just to talk about it. The light year, the distance light travels in a year, which is nearly 6 trillion miles. The nearest stars were several of those away. The universe had just become almost frighteningly large, and parallax had handed us the first rung of a ladder we would spend the next century climbing. Before we climbed that ladder higher, there was a different question worth answering, because it had been considered literally impossible. And the answer to it is one of the most beautiful turns in the whole story. What are the stars actually made of? It seems like a question we could never answer, since we can never go to a star, never bring back a sample, never touch one. A famous philosopher had declared in the early 1800s that the chemical makeup of the stars was something humanity would never, ever know. He was wrong within decades, and the key was light itself. When you pass starlight through a prism and spread it into a rainbow, that rainbow turns out to be crossed by dark lines, gaps where specific colors are missing. Each chemical element, when present in a star's outer layers, absorbs its own exact set of colors, leaving a unique pattern of dark lines, a barcode. So, by reading the barcode in a star's light, you can tell exactly which elements are in it from across unimaginable distances without ever leaving the Earth. The light carries the recipe. For a long time, astronomers assumed that the stars and the sun must be made of roughly the same stuff as the Earth, mostly rock and metal, because that seemed only natural. Then, in the year 1925, a young researcher at Harvard named Cecilia Payne worked through the starlight barcodes far more carefully than anyone had before, taking into account how temperature changes which lines show up, and she reached a conclusion that was so surprising that the senior astronomers of the day pressured her to soften it in her thesis. She had found that the stars are not made of the same stuff as the Earth at all. They are made overwhelmingly of the lightest, simplest element there is, hydrogen, with helium second, and everything else, all the heavier elements, amounting to barely a trace. The sun and nearly every star is a giant ball of the simplest atoms in the universe. She was right, and the men who doubted her admitted it a few years later. It turned out that the universe is built mostly out of its plainest ingredient, and figuring that out from nothing but the colors of starlight is one of the quiet masterpieces of 20th century science. Reading starlight this way did more than reveal what stars are made of. It let astronomers sort the stars and, eventually, understand their entire lives. When you plot stars by their true brightness and their color, which is really their temperature, they do not scatter randomly. Most of them fall along a single sweeping band, with a few odd groups off to the sides, and that pattern, once understood, turned out to be a map of how stars are born, live, and die. A star is a tremendous ball of mostly hydrogen, so heavy that its own gravity crushes its core to a temperature of millions of degrees, hot enough to force hydrogen atoms to fuse together into helium, releasing enormous energy in the process. That energy, pushing outward, is the only thing holding the star up against the crushing inward pull of its own gravity, and the long, stable middle of a star's life is simply the standoff between those two, gravity pulling in, fusion pushing out, held in balance for millions or billions of years. Our own sun has been doing this for around 4.5 billion years and has roughly that long again to go. But the balance cannot last forever, because eventually the star runs low on hydrogen fuel in its core, and when it does, the story turns dramatic, and the ending depends almost entirely on how heavy the star is. A star, like our sun, when it runs low, will swell up enormously into a red giant, bloating out until it swallows its nearest planets, then gently shrug off its outer layers into a beautiful, expanding shell of glowing gas and settle down as a small, dense, slowly cooling ember called a white dwarf, a dead star about the size of the earth, but so compressed that a spoonful of it would weigh tons. The far heavier stars go out in a vastly more violent way. When a giant star finally runs out of fuel, its core collapses in a fraction of a second, and the star detonates as a supernova, an explosion so bright that for a few weeks it can outshine an entire galaxy of billions of ordinary stars. And here's the part that connects all of this directly to you. The heavy elements, the carbon in your cells, the oxygen you breathe, the iron in your blood, the calcium in your bones, none of these existed in the early universe, which was almost pure hydrogen and helium. They were forged inside stars and in the fury of those explosions, and then scattered across space to become part of new stars, new planets, and eventually living things. The often repeated line that we are made of stardust is not poetry, it is laboratory fact. Every atom in your body, heavier than helium, was cooked inside a star that died before the sun was born. Before we follow the distance ladder out to the galaxies, it is worth turning our attention to the single most studied object in the entire sky, and also the closest, the one that has shaped human life more than any star, our moon. People have watched the moon more carefully and for longer than anything else above us, because it does something no star does. It changes night by night in a steady, reliable rhythm, growing from a thin sliver to a full bright disk and shrinking away again over about a month. And that cycle gave humanity its first calendar. The word month itself comes from the moon. For a long time, the changing shape was a mystery, but the explanation turns out to be simple and rather beautiful. The moon does not make its own light. It only reflects sunlight, and at any moment, exactly half of it is lit, the half facing the Sunday. What changes is how much of that lit half we can see from our angle here on Earth as the moon travels around us. When the moon is on the far side of us from the sun, we see its whole lit face, a full moon. When it sits between us and the sun, the lit side faces away, and we see only darkness, a new moon. The phases are not the Earth's shadow, as people often think. They are just a matter of perspective, of how much of the sunlit half is turned toward us. The Earth's shadow does have its moment, though, and that is during an eclipse, which is one of the most dramatic sights the sky ever offers, and which terrified people for most of history. There are two kinds. In a lunar eclipse, the Earth passes directly between the sun and the moon, and the Earth's shadow falls across the moon, often turning it a deep, eerie red, as the only sunlight reaching it is bent through the edges of our atmosphere, the same reddening that colors a sunset. In a solar eclipse, the order is different, with the moon passing directly between us and the sun and blotting it out, turning day briefly to an unearthly twilight. And here there is a coincidence so striking that it almost seems arranged. The sun is about 400 times wider than the moon, but it also happens to be about 400 times farther away, which means that, seen from the Earth, the two appear almost exactly the same size in the sky. That is why the moon can cover the sun so precisely during a total eclipse, hiding its blazing disk while leaving its faint outer atmosphere glowing around the edge. There is no deep reason for this match. It is a fluke of where we happen to be in history, because the moon is slowly drifting away from us, and in the distant past it appeared larger, and in the far future it will appear too small to cover the sun at all. We are living in the brief window of cosmic time when perfect total eclipses are possible, which is a strange and lovely thing to realize. A natural question is why we do not get an eclipse every single month, since the moon goes around us monthly and passes roughly between us and the sun each time. The answer is that the moon's path is tilted slightly compared to the Earth's path around the sun. So most months, the moon passes a little above or a little below the exact line, and its shadow misses us, or our shadow misses it. Only when the alignment is just right do we get an eclipse, which is why they are special events rather than monthly ones. The ancient Babylonians, with their centuries of patient records, worked out the rhythm of these alignments well enough to predict eclipses long before anyone understood what caused them, and being able to forecast the terrifying disappearance of the sun was a tremendous source of power for those who could do it. The moon does more than light our nights and stage eclipses. It pulls on us, and you can watch the result twice a day at any coastline, in the rise and fall of the tides. The moon's gravity tugs hardest on the side of the earth nearest to it, pulling the oceans into a slight bulge. And, in a way that surprises most people, it also creates a second bulge on the far side because the solid earth itself is pulled slightly toward the moon more strongly than the water on the far side is, leaving that water behind in a bulge of its own. So there are two tidal bulges on opposite sides of the earth, and as our planet spins underneath them each day, any given coast passes through both, which is why most places get two high tides and two low tides every day. And there is a slow, remarkable consequence of all this rubbing and pulling. The tides act like a gentle brake on the Earth's spin, very gradually slowing our rotation so that the day is getting slightly longer over millions of years. And at the same time, the moon is slowly spiraling away from us, drifting a few centimeters farther each year. The length of a day and the distance to the moon are always changing, far too slowly to notice in a lifetime, but real. Where the moon came from is its own surprising story. For a long time, nobody could agree, but the picture most scientists now favor is dramatic. In the chaotic early days of the solar system, more than 4 billion years ago, a young planet about the size of Mars is thought to have slammed into the early Earth in a colossal collision, blasting a huge amount of molten debris into orbit. And that ring of debris gradually gathered itself together to form the moon. If that is right, then the moon is, in a sense, a piece of the early Earth that got knocked loose and never came back down, which is why the rocks the astronauts brought back from it are so similar to rocks here. The moon is less a separate world than a long-lost relative. Long before any of this was understood, the sky was woven deeply into human life everywhere on Earth, in ways that go far beyond a few famous astronomers. All across the ancient world, people built monuments aligned to the heavens. The great stone circle at Stonehenge, raised thousands of years ago, lines up with the rising of the sun at the summer solstice and its setting at the winter solstice. A vast calendar built in stone by people with no writing. Cultures on every continent tracked the sun, moon, and stars to know when to plant, when to harvest, and when to hold their sacred days. Because before clocks and calendars, the sky was the only reliable timekeeper there was. Across the open Pacific, Polynesian navigators learned to read the rising and setting points of particular stars so precisely that they could steer canoes across thousands of miles of empty ocean, finding tiny islands by the sky alone, a feat of practical astronomy as impressive as anything done in an observatory. And sometimes those ancient skywatchers recorded things that would only make sense to us much later. In the year 1054 of the Common Era, Chinese astronomers carefully noted the sudden appearance of a brilliant new star in the sky, a guest star, as they called it, so bright that it was visible in daylight for weeks before slowly fading away over months. For centuries, that record was just a curiosity. But when modern astronomers pointed their telescopes at the exact spot in the sky those old records described, they found a beautiful, expanding cloud of glowing wreckage, the shredded remains of a star that had blown itself apart, which we now call the Crab Nebula. The guest star the Chinese saw nearly 1,000 years ago was a supernova, the death explosion of a giant star, and at the very center of that wreckage sits a spinning neutron star, a pulsar, the crushed core left behind, a 1,000-year-old note scribbled by astronomers who had no idea what they were seeing, turned out to be an eyewitness account of one of the most violent events in the universe, and it let us connect their night to ours. That is the strange gift of astronomy, that the sky keeps records too, and if you learn to read them, the past is still up there waiting. Before we leave our own corner of space for the deep universe, it is worth staying close to home for a while, because our own solar system held its own surprises, and the way we came to understand it is a story all by itself. For most of history, the objects that scared people most in the sky were comets, those rare visitors that appear out of nowhere, hang in the sky for weeks, trailing a ghostly tail, and then vanish. They were taken as omens, signs of disaster, the death of kings. The man who tamed the comet was the same Edmund Halley who paid to publish Newton's great book. Halley took Newton's brand new law of gravity and applied it to the records of past comets, and he noticed that a bright comet seen in his own lifetime followed almost the same path as comets recorded decades earlier, at regular intervals of about 76 years. He realized they were not separate visitors at all, but a single comet, returning again and again on a long, stretched orbit around the Sunday. He predicted it would come back around the year 1759. He did not live to see it, but the comet returned right on schedule years after his death, and it has carried his name ever since. A thing that had been a symbol of dread for all of human history turned out to be just another object obeying the same gravity as a falling apple, keeping an appointment it could not break. The solar system kept growing and changing as our instruments improved. We found a whole belt of rocky rubble between Mars and Jupiter, the asteroids, thousands upon thousands of them, leftover building material that never managed to form a planet. In the year 1930, a young astronomer named Clyde Tombaugh, painstakingly comparing photographs of the sky taken on different nights to spot anything that moved, found a faint, slow-moving dot far beyond Neptune, and it was hailed as the ninth planet, Pluto. For most of a century, school children learned 9 planets. But as telescopes got better, astronomers began finding more small icy worlds out in that distant region, some nearly as big as Pluto, and they realized Pluto was not a lonely ninth planet at all, but one of the larger members of a whole swarm of icy bodies out past Neptune, now called the Kuiper Belt. In the year 2006, this led to one of the most famous demotions in science, when astronomers redefined what counts as a planet and reclassified Pluto as a dwarf planet. A lot of people were upset about it, which tells you something nice about how attached we get to the map of the sky we grew up with. Far beyond even the Kuiper belt, we think there is a vast spherical cloud of icy chunks called the Oort cloud, surrounding the whole solar system like a shell so distant that the long period comets that fall from it take thousands of years to swing around the sun and back. For all of this history, though, every world beyond the Earth was just a point or a small disk seen from far away, studied only through a telescope. That changed suddenly and completely in the second half of the 20th century, when, for the first time in the history of life on Earth, something from our planet left it. The space age opened in the year 1957, when the first artificial satellite was placed into orbit, a small metal sphere beeping overhead, and within a few decades, we had walked on the moon and sent robotic spacecraft to every single planet in the solar system. This matters enormously for astronomy because it turned the planets from lights in a telescope into places. We flew past Jupiter and saw a storm bigger than the Earth that has been raging for nearly 2 centuries. We saw the rings of Saturn up close, made of countless chunks of ice. We landed on Mars and found dry riverbeds and the chemistry of ancient water. A pair of probes called Voyager, launched in the 1970s, took a grand tour past the outer planets and then kept going, and they are still traveling now, having crossed beyond the edge of the sun's influence into the space between the stars, the first human-made objects ever to do so. On its way out, one of them turned its camera back toward home and took a photograph of the Earth from billions of miles away, in which our entire planet, everyone who has ever lived, is a single, almost invisible point of pale light, smaller than a single pixel, hanging in the dark. It is a humbling thing to see, and it is the kind of perspective only astronomy can give you. While we were exploring our neighborhood, astronomers were also trying to map the much larger structure we live inside, the Milky Way itself, the galaxy that holds our sun and a few 100 billion other stars. When you look up at a truly dark sky and see that faint band of light arching overhead, the band that gives the galaxy its name, you are looking edge on through the flattened disk of our own galaxy, seeing the combined glow of countless distant stars, too faint to pick out one by one. For a long time, people assumed that we sat near the center of this great pinwheel of stars, because that is the comfortable, natural assumption, the same one that had put the Earth at the center of everything. In the early 1900s, the astronomer Harlow Shapley set out to actually measure where we are by mapping the positions of dense balls of ancient stars called globular clusters, which orbit the galaxy. He found that these clusters were not spread evenly around us, as they would be if we were central, but were bunched off heavily to one side, all clustered around a point far from the sunday. The only sensible reading was that the true center of the galaxy lay in that direction, tens of thousands of light years away, and that we are not at the center at all. We live in the quiet suburbs, far out along one of the spiral arms, looking in toward a distant, crowded downtown we cannot even see clearly because of all the dust in the way. It was the same lesson Copernicus had taught, only bigger. First, the Earth was not the center of the solar system. Now, the sun was not the center of the galaxy. Every time we measured carefully, we found ourselves further from the middle of things, and that has been one of the great running themes of astronomy ever since. This raised the obvious next question, the one that would split astronomy down the middle. If our galaxy is this enormous wheel of hundreds of billions of stars, and we are stuck off in one corner of it, then what are those faint spiral smudges scattered across the sky? Were they small clouds of gas inside our own galaxy, or were they other galaxies entirely, separate islands of stars so far away that all their billions of suns blurred into a single faint patch? Nobody could say, because nobody could measure how far away they were. And that question, the size of the universe itself, is exactly where the next great chapter begins. There is one star we have studied more than all the others combined, and it is so familiar that we forget it is a star at all, which is our own Sunday. It is easy to think of the sun as something different from the stars of the night, but it is exactly the same kind of object, an ordinary star that happens to be close. Every other star you can see is a sun like ours, just so far away that it shrinks to a point, and our sun would look like just another faint dot if you backed away a few light years. Because it is right next door, the sun is the one star we can examine in real detail, and what we see is a colossal ball of mostly hydrogen, so large that you could fit more than 1 million Earths inside it, with a core squeezed so hard by its own gravity that hydrogen fuses into helium there, releasing the energy that has kept it shining for around 4.5 billion years. The light and warmth falling on you right now was made in that core, though the energy takes an astonishingly long time to fight its way out from the center to the surface before finally escaping as sunlight and crossing to us in 8 minutes. The sun is not the calm, steady lamp it appears to be. Its surface churns and boils, and it is marked by sunspots, darker patches that are actually slightly cooler regions where the sun's tangled magnetic field pokes through. The number of these spots rises and falls in a cycle of about 11 years, a kind of slow heartbeat of solar activity. The sun also constantly blows a thin stream of particles out into space called the solar wind, and now and then it hurls out a violent burst of them in an enormous eruption. When that storm of particles reaches the Earth, our planet's magnetic field funnels them toward the poles, where they crash into the upper atmosphere and make it glow, which is what causes the shimmering curtains of the northern and southern lights, the auroras. The same outbursts can also disrupt satellites, radio signals, and power grids, so studying the sun's moods, what we now call space weather, has become a practical necessity for a world that runs on electronics. Our nearest star is not just a source of warmth. It is a slightly temperamental neighbor whose storms we have learned to watch. And the sun, like every star, will not last forever. In around 5 billion years, it will run low on the hydrogen fuel in its core, and when it does, it will swell into a red giant, bloating outward until it likely swallows the inner planets and scorches the earth to a cinder. Then it will shed its outer layers into a glowing shell of gas and settle down as a white dwarf, a dim, dense ember slowly cooling over billions of years. This is not a guess about one special star. It is the ordinary life story of a star like ours, written in the night sky all around us. where we can see other stars at every stage of that journey, from newborn to bloated giant to faint, dying ember. The sun's future is on display in the present, scattered across the sky in the lives of its cousins. Knowing what the sun is did not, by itself, tell astronomers how far away it is, and that turned out to be one of the hardest and most important measurements in the whole field, because the distance from the Earth to the sun is the yardstick for the entire solar system. Kepler's laws gave the relative distances of all the planets, telling you, for instance, that one planet was a certain number of times farther from the sun than another, but they could not give the actual mileage, the true size of the whole arrangement, pin down one real distance, and all the rest would snap into scale. The clever method astronomers settled on was to watch the planet Venus pass directly in front of the sun, a rare event called a transit, and to time it precisely from widely separated places on the Earth. Observers far apart see Venus cross the sun along slightly different paths, and from that difference, with careful geometry, you can triangulate the distance. The catch was that these transits are rare, coming in pairs separated by more than a century. So when one was due in the 1700s, nations mounted expeditions to the far corners of the globe to observe it, sending astronomers on long and dangerous sea voyages just to time a small black dot crossing the Sunday One famous voyage to the Pacific carried instructions to observe the transit before going on to chart unknown coasts. It was one of the first great international scientific campaigns, with people scattered across the planet, all watching the same event to measure the size of the heavens. Much later, we pinned the distance down with great precision by bouncing radar off Venus and timing the echo. But the transit expeditions were a heroic early answer to the question of how big our own corner of space really is. And the answer is about 93 million miles to the Sunday. None of this would have been possible without the slow improvement of the one tool that defines astronomy, the telescope, and the story of how it grew is worth telling, because every leap in what we could see came from a leap in how we gathered light. The very first telescopes, including Galileo's, worked by bending light through glass lenses, and they were small and flawed, with the lenses splitting light into annoying colored fringes that blurred the view. To see more, astronomers built bigger and bigger lens telescopes, but large lenses sag under their own weight and are hard to make flawless, so this approach hit a wall. The breakthrough was to gather light with a curved mirror instead of a lens, an idea Newton built into the first reflecting telescope, and mirrors turned out to be far easier to make large. From then on, the history of astronomy was, in large part, a race to build ever bigger mirrors, because a bigger mirror catches more light and reveals fainter, more distant objects. The great telescopes of the 20th century, with mirrors many feet across, were the ones that let Hubble find his galaxies and measure the expanding universe. But there was a stubborn problem that no amount of mirror could fix, which is the Earth's own atmosphere. The air above us is always moving and shimmering, and that is what makes stars twinkle, charming to the eye, but ruinous for a telescope, because it smears fine detail into a blur. Astronomers found two ways around it. The first was to build telescopes that can measure the blurring hundreds of times a second and bend a flexible mirror to cancel it out in real time. A clever trick called adaptive optics that lets ground telescopes see almost as sharply as if the air were not there. The second, more drastic, was to leave the atmosphere behind entirely by putting telescopes into space, above all the shimmering air, which is exactly why the great space telescopes can see so much more clearly than anything on the ground, and why we send them up despite the enormous cost. And in the most recent trick of all, astronomers learned to link separate telescopes together, combining their signals so that dishes scattered across continents act as a single instrument, as wide as the distance between them. That is how a network of radio dishes spread around the planet was able to act like a telescope the size of the Earth and capture the very first image of a black hole. The whole arc, from Galileo squinting through a small glass tube to a planet-sized virtual telescope photographing the edge of a black hole, is really the story of one simple thing: our endless effort to gather just a little more light from just a little farther away. So, by the early 1900s, astronomers could measure the distances to nearby stars by parallax. They knew what stars were made of, and they were beginning to understand how stars live and die. But parallax only reaches so far. The wobble it depends on gets smaller and smaller with distance until it shrinks below what any telescope can detect, and beyond a few hundred light years, it simply runs out. The stars stretched out far past that limit, and so did fuzzy patches of light called nebulae, and nobody could say how far away those were or even what they were. That uncertainty set up one of the biggest arguments in the history of the field, an argument about nothing less than the size of the entire universe. The breakthrough that would eventually settle it came, fittingly, from someone who was barely allowed to do astronomy at all. At Harvard, around the turn of the century, much of the painstaking work of measuring stars on photographic plates was done by a group of women hired as human computers, paid little and given almost no credit, because the men who ran observatories did not think women belonged behind the telescopes. One of them was named Henrietta Leavitt, and while studying a particular kind of star that pulses, growing brighter and dimmer on a steady cycle called a Cepheid variable, she noticed something that would crack the universe wide open. She found that for these pulsing stars, the length of the cycle was tied directly to the star's true brightness. The ones that pulsed slowly were genuinely, intrinsically brighter, and the ones that pulsed quickly were fainter, in a precise, predictable relationship. This sounds like a small technical detail. It is one of the most important discoveries in the history of astronomy, and here is why. If the speed of a Cepheid's pulse tells you how bright it truly is, then you have found a kind of cosmic measuring candle. You watch the star pulse, you time the cycle, and that tells you its real intrinsic brightness, its actual wattage. Then you look at how bright it merely appears in your telescope, And since things look fainter the farther away they are, in a known way, the gap between how bright the star truly is and how bright it appears tells you exactly how far away it must be. It is the same instinct you use when you see a light that you know is a street light looking dim and conclude it must be far off. Leavitt had handed astronomy a way to measure distances far, far beyond the reach of parallax, anywhere a Cepheid could be found. She had built the next rung of the ladder, and she did it as an underpaid assistant who was not permitted to pursue the implications herself. She died before the full power of her discovery became clear. That power became clear in a famous clash in the year 1920, sometimes called the Great Debate. Two respected astronomers stood up and argued opposite sides of an enormous question, which was whether the Milky Way, our own collection of stars, was the entire universe or just one island among many. One of them, Harlow Shapley, argued that the spiral-shaped nebulae, those fuzzy pinwheels of light, were relatively small clouds within our own galaxy, and that our galaxy was essentially everything there was. The other, Heber Curtis, argued that those spirals were separate galaxies in their own right, vast cities of stars like our own, unimaginably far away. The debate could not be settled that day because nobody yet had a way to measure how far away the spirals were. The question hung in the air, waiting for someone to bring a measurement instead of an argument. The someone was Edwin Hubble, working with the largest telescope in the world at the time, on a mountain in California. In the years just after the debate, Hubble managed to pick out individual Cepheid variable stars inside the Great Spiral in the constellation Andromeda, and he applied Leavitt's method. He timed their pulses, read off their true brightness, compared it to how faint they appeared, and calculated the distance. The number he got was so large that it ended the argument completely. The Andromeda Spiral was far, far outside our own galaxy, hundreds of thousands of light years away, much farther than the entire width of the Milky Way. It was not a cloud within our galaxy at all. It was another galaxy, a separate island of billions of stars. And if it was, then so were all the other spirals. In a single stroke, the universe went from being one galaxy to being a vast ocean containing countless galaxies, each one a Milky Way of its own, scattered across distances that dwarfed anything imagined before. We now think there are something like 2 trillion galaxies in the observable universe. Before Hubble's measurement, in living memory, educated people thought our one galaxy might be all of creation. Leavitt's pulsing stars had shown them an ocean, and Hubble was not done, because once he could measure distances to galaxies, he noticed something even more startling about them. He compared the distances of galaxies to the colors of their light, and he found that almost all of them were slightly reddened in a particular way, the way a sound drops in pitch as it speeds away from you, which for light means the object is receding. Nearly every galaxy was rushing away from us, and the farther away a galaxy was, the faster it was fleeing. There was only one sensible way to read this. The whole universe is expanding, with every galaxy racing apart from every other, like raisins in a loaf of bread that is rising in the oven, each raisin drifting away from all the others as the dough between them swells. This was the discovery that, run backward in time, points to a hot, dense beginning, the idea we now call the Big Bang, the notion that the whole universe started in an incredibly compact, hot state nearly 14 billion years ago and has been expanding ever since. The light from distant galaxies, then, is not only old, it is stretched, carrying the record of how long it has been traveling through an expanding cosmos. Astronomy had found, almost by accident, that the universe has a history, a beginning, and an age. This also gave astronomers the highest rungs of the distance ladder. For the closest objects, parallax. Beyond that, Leavitt's Cepheid candles. Beyond even those, where individual stars blur away, astronomers use whole exploding stars, certain supernovae that always detonate with very nearly the same true brightness. So, they work as even brighter standard candles, visible across billions of light years. And beyond that, the stretching of the light itself, the amount a galaxy's colors are shifted, tells you how far its light has traveled. Each method is calibrated against the one below it, like a ladder where each rung is anchored to the last, reaching from a finger held at arm's length all the way out to the edge of the visible universe. That ladder, built over centuries by Eratosthenes and Bessel and Leavitt and Hubble and many others, is how we know the distance to anything in the sky. It is the answer to the child's question, and it took us 2,000 years to build it. For most of this story, astronomers had only one way to study the heavens, which was to collect visible light, the same light our eyes use, just gathered by bigger and bigger mirrors. But visible light is only a thin slice of a much broader spectrum, and the rest of that spectrum was about to open up entirely new windows on the universe, revealing things that are completely invisible to the eye. The first of these windows opened almost by accident in the 1930s, when an engineer named Karl Jansky, working for a telephone company and trying to track down sources of static that interfered with radio calls, found a faint hiss that rose and set with the stars coming from the direction of the center of our own galaxy. He had detected radio waves from space. The sky, it turned out, was not just glowing in visible light. It was also broadcasting in radio, and once astronomers built dishes to listen, they heard a universe full of things the eye could never see, from the violent cores of distant galaxies to the cold clouds of gas where new stars are born. That same broadening of vision led to one of the most important discoveries of the 20th century, the discovery of the actual afterglow of the Big Bang. If the universe really began hot and dense, then there should be a faint warmth left over, soaking the whole sky from every direction, stretched out by billions of years of expansion into a dim hiss of microwaves. In the year 1965, two researchers found exactly that, again partly by accident, while trying to get rid of a persistent noise in a radio antenna that they could not eliminate no matter what they did. The noise was not a fault in their equipment. It was the oldest light in existence, the leftover glow from when the universe was only a few 100,000 years old, arriving at the Earth from all directions at once. We had detected the faint echo of the beginning of everything, and it remains the strongest single piece of evidence we have for how the universe started. As technology improved, astronomers learned to see the sky in every kind of light. They built telescopes for infrared, the heat radiation that lets us peer through clouds of dust to the stars forming inside them. They built telescopes for ultraviolet, for X-rays, and for gamma rays, the most energetic light of all, which reveal the hottest and most violent objects in the universe, the gas swirling around black holes and the explosions of dying giant stars. Because X-rays and many other kinds of light are blocked by the Earth's atmosphere, this meant putting telescopes into space, above the air, where they could see clearly. And in the most recent chapter, astronomy has begun to study the sky without using light at all. In the year 2015, instruments finally detected gravitational waves, tiny ripples in the fabric of space itself, set off by the collision of two black holes more than 1 billion years ago, a kind of cosmic tremor passing through the Earth and stretching it by less than the width of an atom. For the first time, we were not looking at the universe, we were feeling it. While these new windows were opening, one very old question was finally getting an answer, a question people had wondered about since they first realized the stars were other suns. Are there other planets out there, worlds going around other stars? For all of history, this had been pure speculation, because a planet around another star is hopelessly faint, lost in the overwhelming glare of the star it orbits, like trying to spot a firefly next to a searchlight from miles away. The trick that finally worked was to watch the star instead of the planet. A planet, as it orbits, tugs very slightly on its star with its own gravity, making the star wobble by a tiny amount, and that wobble shows up as a small, regular shift in the colors of the star's light. In the year 1995, two astronomers named Michel Mayor and Didier Queloz detected exactly such a wobble in a sun-like star called 51 Pegasi, and announced the first planet ever found around another ordinary star. It was a strange world, a giant the size of Jupiter but whipping around its star in just a few days, far closer than anyone expected a big planet could be. For that discovery, they were later given the Nobel Prize. That first planet opened the floodgate. Astronomers developed another method, watching for the tiny dip in a star's brightness when a planet passes directly in front of it, blocking a sliver of its light, and they pointed dedicated telescopes at hundreds of thousands of stars at once to catch these dips. The result is that in only about 30 years, we have gone from knowing of 0 planets outside our solar system to having confirmed thousands of them, with many thousands more waiting to be checked, and the clear conclusion that planets are not rare at all. Most stars in the sky, it seems, have planets, which means our galaxy alone holds billions upon billions of worlds. Some of them orbit at just the right distance from their star for liquid water to be possible in what astronomers call the habitable zone, the band that is neither too hot nor too cold. We do not yet know whether any of them carry life, and that is one of the great open questions of our time. But the sheer number of worlds has transformed the question from a lonely fantasy into a careful search. Through all of this, the telescope itself kept growing, both on the ground and in space. And two space telescopes in particular changed what humanity could see. The first, named after Edwin Hubble, was placed in orbit above the blurring effect of the atmosphere, and for decades it sent back images of staggering depth and clarity. In one famous experiment, astronomers pointed it at a patch of sky that looked completely empty, a spot no bigger than a grain of sand held at arm's length, and let it stare for days. That tiny, seemingly blank patch filled up with thousands of galaxies, each one holding billions of stars in a direction where the eye sees nothing at all. It was a humbling demonstration that the universe is full, that there is essentially no empty direction, that wherever you look deeply enough, you find more galaxies stretching back toward the beginning of time. The most recent and most powerful of these eyes is the James Webb Space Telescope, launched at the end of the year 2021 and stationed about 1 million miles from Earth, far beyond the moon. It is built to see in infrared, which lets it do something remarkable. Because the light from the most distant galaxies has been traveling for so long and stretched so much by the expansion of the universe that it has been shifted out of visible colors entirely and into the infrared. By catching that stretched, ancient light, Webb can see galaxies as they were in the first few 100 million years after the Big Bang, looking back across more than 13 billion years to a time when the first stars and galaxies were just switching on. When we look through it, we are looking almost all the way back to the beginning, seeing baby galaxies as they actually were when the universe was young, their light only now arriving after a journey longer than the age of the Earth. These new ways of seeing the sky did not just sharpen the old picture, they turned up objects nobody had ever imagined, things so strange that when they first appeared in the data, astronomers assumed something had gone wrong with the equipment. In the year 1967, a young researcher named Jocelyn Bell, studying signals from a radio telescope, found a source in the sky that pulsed with astonishing regularity, a sharp tick repeating every second or so, steadier than almost anything in nature. It was so regular and so artificial seeming that, half joking, the team labeled the first one with the nickname Little Green Man, wondering for a moment whether they had stumbled onto a signal from another civilization. They had not. What she had found was a pulsar, the spinning corpse of a dead giant star, a city-sized ball so dense that the matter of an entire star heavier than the sun is crushed into a sphere you could drive across in an hour, spinning many times a second and sweeping a beam of radio waves around like a lighthouse, so that we catch a tick each time the beam points our way. A spoonful of the stuff it is made of would weigh as much as a mountain. We had found the dead, dense remains that giant stars leave behind, and they behave like nothing else in the universe. Around the same time, astronomers found something at the opposite extreme, not dead and dense, but blazing and impossibly bright. Certain faint points of light, which looked like ordinary stars, turned out, when their light was carefully read, to be enormously far away, billions of light years off, and yet still visible, which meant they had to be shining with the power of hundreds of ordinary galaxies, all packed into a region not much larger than our solar system. They were named quasars, and for a while they made no sense at all, because nothing known could produce that much light from so small a space. The answer turned out to be the most extreme object in all of physics, a supermassive black hole, a region where so much mass has collapsed that gravity has sealed off a piece of space from which not even light can escape. A quasar is the brilliant, searing glow of gas heated to enormous temperatures as it spirals down towards such a black hole, a death cry of matter at the edge of the point of no return. And these monsters are not rare. We now believe that nearly every large galaxy, including our own Milky Way, has a giant black hole sitting at its center, millions or billions of times the mass of the Sunday. We have watched stars near the center of our own galaxy whip around something unseen and incredibly heavy at tremendous speeds, tracing tight orbits around a point that gives off almost no light, and the only thing that could anchor those orbits is a black hole about 4 million times the mass of the Sun, sitting silently at the heart of the Milky Way. For a long time, a black hole was something we could only detect indirectly by its pull on things around it, because by its very nature, it gives off no light to see. Then, in the year 2019, an extraordinary project called the Event Horizon Telescope did something that had seemed impossible by linking radio dishes from all over the planet together so that they acted like a single telescope nearly the size of the Earth. Astronomers managed to capture an actual image of the shadow of a black hole, a dark circle ringed by the glow of superheated gas at the center of a galaxy 55 million light years away. A few years later, they released an image of the black hole at the center of our own galaxy as well. For the first time in history, we had a photograph of the one object that supposedly cannot be photographed, the silhouette of a hole in space itself. It looked almost exactly the way the equations of general relativity, written down a century earlier, had said it should. But the strangest discoveries of modern astronomy are not the bright objects or the dense ones. They are the things we cannot see at all and yet can prove are there. In the 1970s, an astronomer named Vera Rubin set out to do something that sounds routine, which was to measure how fast the stars in other galaxies orbit around their centers. By the rules of gravity, the stars far out at the edge of a galaxy, where there is little visible matter, should orbit slowly, just as the outer planets in our solar system move much more slowly than the inner ones because there is less mass pulling on them out there. That is not what she found. She found that the stars at the edges of galaxies were moving just as fast as the ones near the center, far too fast for the visible matter to hold on to. By all the laws of gravity, those galaxies should be flying apart, flinging their outer stars into space. They were not. The only way to explain it was that each galaxy is wrapped in an enormous, invisible halo of some unseen material, far more of it than all the visible stars and gas put together, holding the galaxy together with its gravity while giving off no light at all. We call it dark matter, and decades of work have only deepened the mystery because we still do not know what it is. It is not made of ordinary atoms. It does not shine or block light, and despite enormous effort, we have never directly caught a single particle of it. Yet, there appears to be roughly 5 times as much of it as all the ordinary matter in the universe, and without it, galaxies, as we know them, could not exist. The most common stuff holding the cosmos together is something we have never seen. And then, near the very end of the 20th century, came the discovery that may be the strangest of all. Two teams of astronomers were carefully measuring the expansion of the universe by tracking those reliable exploding stars, the supernova standard candles in very distant galaxies. They fully expected to find that the expansion was gradually slowing down over time because the combined gravity of all the matter in the universe should be pulling everything back together, putting on the brakes. Instead, in the year 1998, they found the opposite. The expansion of the universe is not slowing down, it is speeding up. Something is pushing the universe apart, faster and faster, overwhelming the pull of all that gravity, and we have no idea what it is. We have given it a name, dark energy, but the name is just a label for our ignorance. It appears to make up the majority of everything that exists, around 2/3 of the entire universe, and it is causing the cosmos to fly apart at an accelerating rate, carrying the distant galaxies away from us ever faster. So, if you add it all up, everything we can actually see, every star and planet and glowing cloud of gas, is only about 5% of the universe. The rest, the overwhelming majority, is dark matter and dark energy, two things we have detected only by their effects and otherwise do not understand at all. After everything astronomy has achieved, it has arrived at the humbling conclusion that the part of the universe we can see is the small part. There is one more puzzle worth mentioning, because it is so simple a child could ask it, and yet its answer ties together almost everything in this story. Why is the night sky dark? It sounds like a silly question, but consider it for a moment. If the universe were infinitely old and infinitely large and filled with stars in every direction, then no matter where you looked, your line of sight would eventually land on the surface of some star, and the entire night sky should blaze as bright as the Sunday. But it does not. The night is dark, and the darkness itself is telling us something profound. The night is dark because the universe is not infinitely old. It had a beginning only some billions of years ago, so the light from the most distant stars has simply not had time to reach us yet. And because the universe is expanding, the light from the farthest galaxies is stretched and dimmed until it fades from view. The simple darkness between the stars, the thing you see every single night, is itself evidence of the Big Bang and the finite age of everything. The dark sky is not empty, it is a clock. Even now, the story is far from finished, and astronomy has run into a genuine puzzle right at its foundations. When astronomers measure how fast the universe is expanding using the nearby distance ladder, the Cepheid candles, and the supernovae, they get one number. When they measure the same expansion rate a completely different way from the afterglow of the Big Bang and the physics of the early universe, they get a slightly but stubbornly different number. The two measurements should agree, and they do not, and no one has yet found the mistake or the missing piece that would reconcile them. It might turn out to be a subtle error somewhere, or it might be a crack in our understanding, a hint that something about the universe, perhaps the dark energy itself, is behaving in a way our theories do not yet capture. We do not know, and that not knowing sits right at the cutting edge of the field today. Once you accept that the universe is full of galaxies stretching out in every direction, the natural next question is how big it all actually is. And the honest answer is that the numbers stop meaning anything to the human mind fairly quickly. Light, the fastest thing there is, crosses the gap from the sun to the earth in about 8 minutes and crosses our entire solar system in a matter of hours. The nearest star beyond the sun is about 4 light years away, meaning its light takes 4 years to reach us. Our own galaxy, the Milky Way, is roughly 100,000 light years across, so light takes 100,000 years just to cross the city of stars we live in. The nearest large galaxy, Andromeda, is about 2.5 million light years away, and the farthest things we can see are over 13 billion light years off. The observable universe, the sphere of everything whose light has had time to reach us, is something like 93 billion light years across, and that is only the part we can see. The whole universe may well be far larger, perhaps infinite, stretching on beyond anything our telescopes will ever reach. These are not numbers you can really feel. They are just a way of admitting that the universe is unimaginably, almost violently large, and the galaxies that fill all that space are not scattered randomly through it, which is one of the more beautiful discoveries of recent decades. When astronomers map the positions of millions of galaxies, charting how they are arranged across the sky and at what distances, a hidden structure appeared, one that nobody expected. The galaxies are strung together into enormous threads and sheets, long glowing filaments of thousands of galaxies, and these filaments are wrapped around vast, almost completely empty bubbles of nothing, voids hundreds of millions of light years across. The whole arrangement looks, from a distance, eerily like a web, or like the network of cells in a living thing, or the threads of a sponge, with galaxies gathered along the strands and emptiness filling the gaps. We call it the cosmic web, and it is the largest structure there is, the actual shape of matter in the universe at the grandest scale. Our own galaxy sits in a small cluster of galaxies, which sits within a larger collection, which is itself just one outlying piece of an immense supercluster, a single strand in that cosmic web. Once again, we are not at the center of anything. We are out on one of the threads. It helps sometimes to compress the whole history of the universe into something the mind can hold. If you imagine the entire 13.8 billion years since the beginning squeezed into a single year, then the Big Bang happens at midnight on the 1st of January. Our own galaxy forms in the spring. The Sun and Earth do not appear until around late summer, and the dinosaurs come and go in late December. On that scale, all of recorded human history, every empire, every war, every person who ever lived and was remembered, fits into the last few seconds before midnight on the 31st of December. We are very, very new here. The light from a single distant galaxy has often been traveling toward us for longer than the Earth has existed, which means the universe was busy and ancient for billions of years before our planet was even a possibility. The newest chapter of astronomy has begun combining these different ways of seeing into a single, richer picture, and one event in particular showed what that can do. In the year 2017, detectors felt the tremor of gravitational waves, ripples in space, coming from the collision of two neutron stars, those ultra-dense stellar corpses, crashing together in a distant galaxy. But this time, unlike the earlier black hole collisions, the smash also gave off light, and telescopes all over the world swung around to catch it, seeing the glow of the explosion in many kinds of light at once, while also feeling the ripple in space. For the first time, we observed a single cosmic event with both gravity and light together, a way of doing astronomy now called multi-messenger astronomy, like suddenly being able to both see and hear something you could previously only see. And the collision taught us something wonderful, because in its glowing debris, astronomers detected the freshly forged signatures of heavy elements, including gold. It now seems that much of the gold and other heavy metals in the universe, including the gold in a wedding ring or a piece of jewelry, was created in the unimaginable violence of neutron stars colliding. Long ago and far away, the most precious metals on Earth are, quite literally, the shrapnel of dead stars smashing into one another. Through all of this expanding knowledge, one ancient question has stayed stubbornly open, and it may be the one people care about most. Are we alone? For the first time in history, astronomy is in a position to actually go looking for an answer, rather than just wondering. We now know that planets are everywhere, that most stars have them, and that many of them sit in the habitable zone, the band around a star where it is neither too hot nor too cold for liquid water, which is the one ingredient we think life most needs. The newest telescopes can do something that would have seemed like magic a generation ago. When a planet passes in front of its star, A tiny bit of the star's light filters through the planet's atmosphere on its way to us, and the gases in that atmosphere leave their fingerprints in the light. The same kind of barcode that tells us what stars are made of. So, we are beginning to read the air of planets orbiting other suns, looking for the particular mixtures of gases that on Earth are produced by living things. We have not found life. We may not for a long time, and we may never, but the search has moved out of the realm of dreaming and into the realm of careful measurement. And somewhere in the enormous catalog of worlds we are now compiling, the answer may be waiting. Meanwhile, others patiently listen, scanning the sky for any radio signal that carries the mark of intelligence. And so far the great silence holds, which is itself a fact worth thinking hard about. Once Hubble had shown that the spiral nebulae were whole, separate galaxies. Astronomers naturally began to sort and study these island universes, and they found that galaxies come in a few distinct shapes, a classification that Hubble himself worked out and that we still use in updated form today. The most common picture is the one we know best, the spiral galaxy, a flattened, rotating disk with graceful arms winding outward from a bright central bulge, busy with gas and dust and the ongoing birth of new stars. The kind of galaxy our own Milky Way is. Many spirals, including ours, also have a straight bar of stars across their centers and are called barred spirals. These spiral galaxies are, in a sense, the lively ones, still actively making new stars along their arms, glowing blue with young hot suns. Quite different are the elliptical galaxies, which range from nearly spherical balls to stretched out ovals of stars, with no disk and no spiral arms, and these tend to be the old and quiet ones. Elliptical galaxies are typically full of ancient red stars, with little of the gas and dust needed to form new ones, so they have largely stopped making stars and are slowly fading and reddening with age. The largest galaxies in the universe are giant ellipticals, found at the centers of great galaxy clusters, swollen monsters that grew enormous by swallowing other galaxies. And then there are the irregular galaxies, which have no clear shape at all, chaotic and lumpy, often smaller galaxies whose form has been disrupted, sometimes by a close encounter with a larger neighbor, like the Magellanic Clouds that orbit our own Milky Way. The shapes of galaxies are not just a way of cataloging them, but a clue to their histories, because galaxies change and evolve over cosmic time, and the form a galaxy has tells you something about what it has been through. Astronomers now understand that galaxies grow and transform largely through collisions and mergers, and that when two spiral galaxies collide, as we saw the Milky Way and Andromeda may one day do, the orderly disks are scrambled, and the result is often a single, larger elliptical galaxy. So, the elliptical galaxies may be, in many cases, the end products of mergers, the calm aftermath of galactic collisions, while the spirals are galaxies that have, so far, been left in relative peace to spin and form their stars. The shapes scattered across the sky are snapshots of galaxies at different stages of long and sometimes violent lives. And here is the wonderful thing that makes studying galaxy evolution possible at all. The same time machine effect we keep returning to. Because looking far away means looking far back in time. Astronomers can study galaxies at every stage of cosmic history simply by looking at different distances. Nearby galaxies show us the universe as it is now, while very distant galaxies show us what galaxies looked like billions of years ago when the universe was young. By comparing galaxies near and far, astronomers can effectively watch how galaxies have changed over the history of the universe, seeing that the early universe was full of smaller, more chaotic, more actively star-forming galaxies that gradually merged and settled into the grand spirals and ellipticals we see nearby today. We cannot watch a single galaxy evolve because it takes billions of years, but we can do the next best thing, photographing galaxies at all distances and so at all ages, and piecing together the story of how galaxies grow up, like assembling the life story of a tree by studying a whole forest of trees of different ages all at once. It would be wrong to leave the impression that astronomy is a finished science, a settled story of triumphs, because we are in fact living through one of the most exciting and unsettled periods the field has ever seen. With new instruments overturning old assumptions and deep puzzles wide open, the newest and most powerful space telescope, designed to see in infrared light and peer farther back toward the beginning than ever before, has been sending back results that are forcing astronomers to rethink parts of the story. When it looked at the most distant, earliest galaxies, the ones whose light has traveled for more than 13 billion years, it found some of them to be surprisingly large and surprisingly mature for how early they appear, more developed than the simplest models said galaxies should be so soon after the beginning. This does not overturn the broad picture, but it is a genuine surprise that has astronomers busily reworking the details of how the first galaxies formed, a reminder that every time we build a sharper instrument, the universe turns out to be a little stranger than we assume. That same telescope and the methods we explored earlier are also turning the ancient question of whether we are alone from a matter of pure speculation into one of careful measurement. By catching the starlight that filters through the atmosphere of a planet as it passes in front of its star, astronomers can now read the chemistry of the air on worlds orbiting other suns, searching for the particular gases that, on Earth, are produced by living things. We have not found life, and the search is fiendishly hard, requiring us to tease out the faint fingerprint of a planet's atmosphere from the overwhelming glare of its star. But for the first time in history, we have the tools to actually look, to examine distant worlds for signs of life rather than merely wondering. And somewhere in the growing catalog of planets we are studying, the answer to that oldest of questions may eventually be waiting. Astronomy has also gained entirely new senses beyond light, opening windows that did not exist a generation ago. With the detection of gravitational waves, the ripples in space-time set off by colliding black holes and neutron stars, we began to feel the universe rather than only see it, picking up cosmic events that give off little or no light at all. And in a landmark moment, astronomers observed a collision of two neutron stars using both gravitational waves and light at the same time. The first time a single cosmic event was witnessed through two completely different kinds of signal, an approach now called multi-messenger astronomy, like suddenly being able to both see and hear something we could previously only see. Each new way of sensing the cosmos reveals things the others miss, and combining them gives us a richer picture than ever before, with the colliding neutron stars even confirming that such collisions forge heavy elements like the gold that exists on Earth. There are deep puzzles driving the field as well, none sharper than a genuine crisis over the most basic number in cosmology, the rate at which the universe is expanding. As we measure that rate ever more precisely by two independent methods, one based on the nearby distance ladder and one based on the afterglow of the Big Bang, the two answers stubbornly refuse to agree, a discrepancy known as the Hubble tension that has only grown more puzzling as the measurements have sharpened. Either there is some subtle error hiding in one of the methods, or, more excitingly, the disagreement is real and is telling us that something is missing from our understanding of the universe. Some new ingredient or new physics we have not yet grasped. It is one of the hottest unsolved problems in astronomy, and many hope it is the thread that, when pulled, will lead to the next great breakthrough. And the future promises still more, because astronomers are building a new generation of enormous telescopes, both gigantic instruments on the ground with mirrors many times larger than anything before, and new observatories in space, all designed to see fainter, farther, and sharper than ever. These coming eyes on the universe will study the atmospheres of distant worlds in greater detail, peer even further back toward the first stars and galaxies, map the invisible scaffolding of dark matter, and probe the nature of the dark energy tearing the universe apart. The history of astronomy has, again and again, been a history of new instruments revealing a universe far stranger and grander than anyone expected. From Galileo's first small telescope to the giant observatories of today, and there is every reason to think the pattern will continue, that the deepest discoveries about our universe are still ahead of us, waiting for the next astronomer brave enough to point a new kind of eye at the sky and ask what is really out there. And this brings us back to where we started, to that idea of the sky as a time machine. Because the deeper astronomy has reached, the more it has confirmed that we never see the universe as it is now. We only ever see it as it was, with the delay growing longer the farther out we look. The sun, you see, is 8 minutes old. The nearest star is years old. The Andromeda galaxy you can just glimpse on a dark night is being seen as it was around 2.5 million years ago, before our own species existed in its modern form. And the faintest galaxies in Webb's images are being seen as they were before the Earth, the Sun, or even most of the elements in your body had formed. To look out into space is, unavoidably, to look back into time, and the night sky is not a snapshot of one moment, but a single image assembling light from across the entire history of the universe. So, look back over the whole road. It runs from people watching the moon to mark the seasons to a Greek scholar measuring the size of the earth with a shadow to ancient gears that modeled the heavens in brass, to the telescope turning lights into worlds, to the slow, patient building of a ladder of distances that reached from a nearby star out to galaxies billions of light years away. It runs through an underpaid woman's pulsing stars, through the shock of discovering our galaxy is one of trillions, through the realization that the whole universe is expanding out of a hot beginning, and out to the newest telescopes catching light that set off before the Earth was born. Every step was someone refusing to accept that the lights in the sky were simply unknowable, and finding, against all odds, a way to measure them. What I find worth sitting with is how recent almost all of this is. A person whose grandparents are still alive was born into a world that did not yet know there were other galaxies, did not know of a single planet outside our solar system, and had never detected the afterglow of the beginning or felt a ripple in space. In the span of a single long lifetime, we have gone from one galaxy to 2 trillion, from no known worlds to thousands, and from a static sky to an expanding universe with a measurable age. The stars are still just points of light to the naked eye, exactly as they were to the Babylonians on their rooftop. But we now know that each one is a distant sun, that most of them have worlds, that they cook the atoms we are made of, and that the faint smudges between them are other islands of billions of suns, their light reaching us across spans of time longer than the earth has existed. We learned to read all of that off the same sky those first watchers saw. The only thing that changed is that we finally learned how to ask the sky how far and to understand its answer.